Hello and welcome. Today we're doing a question from LeetCode. It's called Koko Eating Bananas. It's medium. We're going to jump right into it. Koko loves to eat bananas. There are n piles of bananas. The ith pile has piles of I bananas. The guards have gone and will come back in H hours. Koko can decide her bananas per hour eating speed of K. Each hour, she chooses some pile of bananas and eats K bananas from that pile. If the pile has less than K bananas, she eats all of them instead and will not eat any more bananas during this hour. Koko likes to eat slowly, but still wants to finish eating all the bananas before the guards return. Return the minimum integer K such that she can eat all the bananas within H hours. So we want to figure out what the most optimal banana eating rate is. We want it to be as slow as possible, but we still want to finish all the bananas before the guards come back in H hours. Example 1, we have 3, 6, 7, 11, and H is 8. Here, the minimum bananas per hour eating rate is 4. So we have 3, 6, 7, 11, and the rate of bananas per hour is 4, which means it's going to take her 1 hour to finish 3 bananas. Even though she finishes early, she can't move on to the next pile because, as per the question, if the pile has less than K bananas, she eats all of them and instead will not eat any more bananas during this hour. So this is going to take 1 hour entirely. Then once we get over here, in 1 hour, she'll finish 4 of the 6 bananas, but she still has 2 more to do. So it's going to be 2 more hours. 7 is going to be another 2. And 11 is going to be 3 hours. It's over 8, but it's less than equal to 12, so it's going to be 3 hours for this pile. So what is our total over here? It's 1 plus 2 plus 2 plus 3, which puts our total at 8, which is great because we want it to stay within the 8 hours. Example 2, we have 30, 11, 23, 4, and 20. So taking a look at example 2, we only have 5 hours to finish all the bananas, and our most optimal rate is going to be 30. So how many hours do we actually take? This first pile is going to be 1 hour. Second pile is also going to be 1 hour. It's under 30. Third is also 1. Fourth is 1. And fifth is also 1. So our total here is going to be 5, and we are within the bound we need to be. And 30 actually in this case would be the maximum rate that we would have been allowed anyway. For any given input, whatever the max input in our array is what the maximum banana eating rate would be. If we went any higher than 30, say we were 35, it would still take us an hour to go through each one, right? So to be as small as possible, but to still get through every single pile in an hour, it would be the max of what we have in our input, in this case, 30. Now looking at example 3, we have 30, 11, 23, 4, 20, and H is 6, and our banana eating rate is 23. So how long will we take for each pile? Our first pile is going to take us 2 hours to finish. There are more than 23 bananas in this pile, but less than equal to 46. Then over here, it's going to take us 1 hour again, 1 hour, 1 hour, and 1 hour. So the total over here is 6. And 23 is going to be our slowest rate possible while making sure we can still finish all the bananas within 6 hours. So we know what our max rate and our minimum rate could be, right? Best possible case, we as slowly as possible will finish 1 banana per hour. And worst possible case would be whatever we have in the maximum of our input. So in this case, our max rate would be 30, here it would be 30, and here it would be 11. Any faster than that, we would still take 1 hour for every single pile. So our slowest rate is 1, and our fastest rate is going to be whatever max we're given. So we have our 2 bounds, and we know we need to find some optimal K between these 2 bounds. That's going to be through trial and error, which means this is a classic binary search problem. For any binary search, we need 2 bounds, and we want to converge at some point within these bounds. So we know we're going to have our 2 bounds, low and high. So let's go ahead and define those. Low and high are going to be 1, and the max of piles respectively. Say we have example 1 over here. For example 1, our low is going to be 1, and our high is going to be the max we have in this input, which is going to be 11. Now we need to find some optimal K between these 2 bounds. So while we haven't converged yet, while low is less than high, we want to find the midpoint. So we're going to do mid equals low plus high, integer divided by 2. Integer dividing this by 2. So what is mid? Mid is going to be 1 plus 11. That's 12. Integer dividing that by 2 is 6. So we're going to try out the rate of 6. At this point, we want to see how many hours it takes if our rate was 6. So we're going to go through every single number in our pile and see how many hours we require. So hours right now is going to be 0. For pile in piles, we're going to add to total what we get by integer dividing the number of bananas we have by our rate. So it's going to be pile integer divided by our rate of mid. And if it doesn't divide evenly, we need 1 extra hour to get the remaining bananas. So if pile mod mid is not equal to 0, if we do have a remainder, we're going to take 1 more hour to complete. So hour plus equals 1. And this actually should be hours. So now we have our hours, and in this example, what would that look like? So our rate right now is 6. It's going to take us 1 hour for the first pile, 1 for the second, 2 for the third, and 2 for the fourth as well. So our total right now is going to be 1 plus 1 plus 2 plus 2, which is 6. But we had 8 hours we could have used, which means we can actually go slower. So if hours is less than equal to h, that means we have plenty of time, we haven't gone out of the time constraint that we have, we can actually get slower. So we're going to move our high down to be our mid. We can get slower. Our high bound for the rate was 11, so we're going to bring that down to bring it slower. And if that's not the case, else, if we don't meet the hour requirement that we need to go faster than what we already have in mid because we haven't met that requirement. So low is going to equal mid plus 1. We need to be faster than what we have. And we'll just keep going in this while loop up until we converge. And in the end, we just need to return whatever we have at low or high. It doesn't matter. They're both going to point to the same thing. And that's going to point to our most optimal rate. So we're just going to return low. So let's go ahead and submit this. And it is accepted. Now, before leaving, let's do a super quick walkthrough, continuing with example 1, just to see how exactly our code is going to run. So continuing where we had left off, we just gone in this for loop and we know the amount of hours we're going to take. That's going to be 6. 6 is less than our input h. Let me write that down as well. So h was 8 over here. 6 is less than equal to h. So we're going to move high down to be middle. High is now going to be 6. Now we go back in this while loop. Low is still less than high and we find a new mid. So 1 plus 6 is 7. Integer dividing that by 2 is 3. We zero out hours, and we're going to recalculate how many hours we're going to take with this new rate. Pile 1 is going to be 1. 2, it's going to take 2 hours. This is going to take 3 hours. And this is going to take 4 hours. So our total right now is 1 plus 2 plus 3 plus 4, which is 10. And 10 is not less than equal to h, so we're going to go in this else. This is because we need to go faster. We're taking longer, right? The guards are going to be back and we're not going to finish all the bananas we need to. So we need to go faster, which means our low point, our low bound is going to move up to mid plus 1. So low is now going to be 4. Going back in this while loop, low is still less than high. We find a new midpoint. So that's going to be 5. We zero out hours again and recalculate. Starting with the first pile, we have 3. 3 integer dividing by 5 is going to be 0, but there is going to be a remainder of 3 if we divide 3 by 5, so it's going to take 1 more hour. For 6, integer dividing that by 5 is going to be 1, but there is a remainder, so this is going to take 2 hours in total. Same with 7, and our last pile is going to take 3 hours in total. So 1 plus 2 plus 2 plus 3, this total sums up to 8, which means this could be a potential rate that we have. So hours is less than equal to h, so we're going to move high to middle. So high is now going to be 5. Going in here one last time, low is still less than high. We calculate our midpoint again. Mid is going to be 4. Hours is 0. We recalculate. This is going to take 1 hour. This is going to take 2 hours. This is going to take 2 hours. And this is going to take 3 hours. Summing this up again is still going to remain 8, which means we're still good on time. So hours is less than equal to h, and we're going to move high down to mid. So high is now going to be 4. Now we can't go back in this while loop. Low is no longer less than high, they're the same. So we exit and we just return low, which is 4. And that is our optimal rate, just as we were expecting. Now talking about space and time complexity. For time, we are doing a binary search. So it's going to be a log-based operation. But every time we do a binary search, we are going to go through every single pile in our input piles. So for time, it's going to be O of n because we are going through every single number as many times as we do our binary search. So n times the number of times we do our binary search, which is going to be dependent on the max of our input. So it's going to be O of n times log of max of piles. And for space, we're only keeping track of a few variables for our binary search, so that's going to be constant O of 1. So we just went ahead and solved Koko eating bananas. If you have any questions with this, of course, let me know down below. I will answer all of them. If this video was helpful, like, comment, share, and subscribe. It really supports the channel. And as always, I will see you in the next one.